Carrying oximeter with your phones.
I felt it pop.
Well, if they get a spirometer in your
paint. You don't even need a spirometer. Somewhere close. I didn't think there was that much paint on the tire, but it had the sound. The best part is, it's for my daughter. There's pink paint. It goes all the way about a quarter mile. It led right into our house.
It goes right. It just looks like a center line, and it just turns right into his driveway. So he's guilty as charged.
I bought a pressure washer this weekend. I washed it at least. The portion around our house, so I can't follow.
At least I can't see the line that goes right into his driveway.
It looks like it's working well.
So is it similar in here, Drew, as the other room?
Yeah.
So the electronics are the same at least?
Yeah, it's fairly similar.
Drew was just saying the offices of Allergy moved from this building to the newer building across the courtyard and over across the street. So probably we'll do all of next year's sessions in the room that we've used occasionally over there.
That big amphitheater room?
No.
No, it's equivalent in size to this. We've used it once or twice when we got bumped out of this building.
Actually, it seems smaller than this room.
I think it is slightly.
Yeah, no, they need to make more room.
The equipment is newer, so I don't think we'll run into these issues.
You're going to teach Dan set up.
Matt and I are going to meet to discuss all that. I think that's a good idea. So I'm out one more time this year. We'll be in Colorado. Actually,
I'm right here next week.
I'll be here. You know who's next week?
It's journal.
It is. Next week is journal.
It is? Somebody here a speaker? Right. So I won't be here to hassle you, so get your hand out.
Right.
Trixie said it's working.
Okay, good.
I'm just going to ask you that. Where are you going?
They even bought new boots yesterday.
Where are you going?
I'm going to go to Breckenridge.
When?
We'll leave on Wednesday afternoon and ski Thursday, Friday, Saturday, come back Sunday. It's going to be spring skiing.
Where are you going?
Breckenridge. No, they have snow, and I haven't skied at all this winter.
It's high enough there. They're okay, too.
It's kind of like, I don't know if it's their last weekend or second last.
I was at Whistler last weekend, and they have one little ribbon of snow down to the village for Beaver Mountain.
So
They have fences bringing you in, but you're dodging big rocks up top. I mean, it's like May, and it's March. It's really pretty discouraging.
When you're about the glacier, isn't there glacier skiing?
Yeah, the glacier, the problem at the bottom of the glacier, though, is the bottom of the glacier, it's got giant ruts in it where the water runs out. So you can ski the top part of the glacier great, but getting out of it is just horrible. So you got to really want to do that. It's a lot of work. So my daughter finally got frustrated. She got some climbing skins, and she just started walking out of bounds and climbing up the peaks and skiing them. Because it's really nice out there. That's why I bought a ticket for it. I don't want to do that. I don't want to walk up this.
Did you get a season ticket this year?
Yeah. Sort of
How much is a season ticket?
It depends on when you get it. If you get it early in the year, they're about $1,100, and if you get it full price, it's $2,000. But at 65, it goes half price. 65 is $699, and at 75, it's $144.
Morning, that room wasn't working.
I got 5 years to go.
But you want to know that
Next year, it's you ski there for 7 days.
on your slides of things you have written, it's not licensed.
Yeah, that's the ticket. You can ski Park City and Deer Valley. My son lives in Park City, and he says that a Park City season pass is $400 more than the multi-area pass, and he can ski the canyons in Park City for $700 or Park City for $1,200. So this is dumb. Yeah, but yeah, that's a really good deal.
Okay. Green today.
Oh, sure. I forgot.
Got my earrings. My sister reminded me.
She's going to wear green, so she's wearing purple and black. So what good was that? Oh, her earrings are green. I was going to say, what good did your sister do reminding you to wear purple and black? Your earrings. Yeah, I saw that. That's really hard. I have a green pen. You can trade me it.
Oh yeah, stuff that grow around.
Even at this
Probably
time.
set the alarm.
Yeah, sure. It wasn't. But it's better than it was at 8:30.
Actually coming over here. Just started. So
Where you going?
used to be like 2 years ago.
How long have you been there?
It's already on.
So pretty tired to you for dad's dog. Tired.
Where you spending most of the time? Tell us.
We're 3 nights in the
I've gotten into electronic medical records.
one night down a lot.
I'll have to get a stride.
Kids were crossing over the
I make everything go twice as long as getting home at 2 o'clock in the morning.
You know, push and shove, I'd retire before doing it.
Or what?
Swimming in the dead
Well, if you don't want to retire now, after you start doing it, you want to.
Everything working.
Good morning. Green shirt.
All right, let's.
I know.
Looks like a lot of people are interested in compliment this morning. Art, you've gotten up early.
I'm not up yet. I just drove half away.
All right, so everybody found it, well, whoever's here found their way to the room change. Just while talking about the logistics, the allergy offices moved from the older building here yesterday over to the newer complex across the street, the building where we've occasionally had to move. So anyway, I think we'll move all of next year's sessions over to that building. Drew points out the newer and the reason we had to move today is the room next door isn't working, somewhat unreliability. Anyway, the word of the day is Cambridge, and Matt is going to give us a review and an update of complement, something we all know perfectly.
We all love.
So Paul asked me if this would all be more clear by the end. Chances are it will be less clear, but you'll know there's a lot more that you don't know than you ever thought. So I have my typical intro slide, and since it's St. Patrick's Day, I can put a little green on. This is sort of, I tried to model this after David's talk, which you probably all remember, which was way too much information to fit into an hour. So we'll see how far we get. But basically, the idea is that what we all know and love about complement, the old stuff, there's actually a lot of new stuff that is a very active area of research. There was a great talk about it at the Quad AI, some of which I've borrowed for this talk at the very end. Nothing to disclose. So here's what I hope to try to get through today. So I'm going to overview the complement cascade, which we all know and love, talk a little bit about the history of that. Review sort of the classic complement deficiencies, again, which we all know and see so often, and then give you some new updates on the classics as to what more we know about it and why it's actually a lot more than you may expect, and then sort of what everybody cites as one of the exciting, expanding roles of complement. There are all these regulatory proteins and how they influence a variety of diseases, which were sort of unexpected from the classical complement stuff, so we'll go through those 4 there. But then at the end, try to spend at least a few minutes on this sort of role reversal. We always think of complement as sort of an effector arm of the adaptive immune system. In reality, I think it's the all-important controller of immunity. Try to convince you on that. And then who'd have thought that actually there's intracellular complement? This was discovered about 1.5 years ago, and how critical that seems to be for T-cell homeostasis. So very briefly, everybody likes to start with some history. I'll just run through this. Kind of at the end of the century before last, it was first discovered that there are these things in your blood that can kill bacteria. In Paris in '96, they discovered 2 separate things. This led to the initial naming of complement as alexin, which it was this heat labile compound that found in blood. It was renamed in the end of that century to complement, specifically because the idea was that it complemented the rest of the immune system, the cellular, the humoral immunity, which is, again, that sort of started this idea that all it is an effector arm of the immune system, which is really not true at all. Then they learned you could split it in '07. I think everybody knows these guys were discovered out of order, and that's why they're named, just to confuse us. The rest of them, I didn't realize this, were actually discovered quite a bit later, which is probably why they were able to get them in order. So as a basic overview, a little problem switching from Mac to PC, I guess, but you have the 3 pathways. Everyone knows this: classical pathway, and I'll walk through this in a little more detail with C1q, RS, C2, and C4. The alternative pathway, which sort of auto-activates with C3 auto-catalyzing itself. And then these all converge at C3, which sort of leads to the terminal membrane attack complex, which carries out the killing of bacteria. In a little more detail, this is a helpful slide. And, everybody has videos and slides and 100 different ways of trying to look at this, and you still never understand it. But here's just another way of how confusing the naming is. You've got this really cool molecule, which I'll show you in more molecular detail in a minute, C1q, which is this really cool hexamer. When it sees antibody, it binds these smaller molecules of C1R and C1S. You have 2 of each. Those are the actual catalytic domains that cleave C2 and C4. And these little pieces fall off. They couldn't name them well, such that you get like C2A, C4A. Instead, you have C2A, C4B, just to make it confusing. But this is the all-critical C3 convertase, which in the alternative pathway is C3b, BB, from factor B, just to be extra confusing. And then if you get down here, you've got your C4b to A3b as the C5 convertase. It's all very great. But basically, this is what was initially discovered, and what gives us sort of the classical roles of complement, which we all know and love, which is really just in host defense. So C3 is critical in that it leads to C3b, which is for optimization of bacteria. Of course, the membrane attack complex, which can actually kill in large part gram-negative bacteria. And then the idea that these factors that float away, the little pieces of C5 and C3, are, in the one case, chemoattractant with C5a, and then as something that increases vascular permeability and degranulation of mast cells and PMNs with C3a. So that's what we all know, just reviewing that. And then basically, when this was all discovered in the 50s, 60s, there was this rush of excitement to find deficiencies in these. And indeed, a deficiency in every one of these proteins has been found. The take-home from this slide, though, is that people sort of lost excitement when they realized how rare these were, though maybe I can convince you otherwise in a moment. So in total, there are 70 C1q deficiencies ever reported, 12 C1R, 8 C1S. Again, just to tell you that for the most part, these are quite rare. A bit more with some of the terminal. I couldn't find firm numbers on how many are out there. Now, that said, we have like 3 C1q deficiencies at Seattle Children's alone, so I'm not entirely sure this is true. There are 2, I think it's worth knowing, that are potentially a lot more common. C2 deficiency, which at least in Caucasian, sort of European descent, has a carrier frequency of 1 in 70, which if you do the math gives you a frequency of about 1 in 10,000 to 1 in 20,000. So it's actually somewhat common. And then C9 in at least some populations is much more common than you may have thought. 1 in 1,000 in Japan, maybe 1 in 5,000 in Korea. And the trick with C9, you may all remember, is that the CH50 is not suppressed. They'll actually have a low normal CH50. Unless you check a C9 level, you're going to miss that. So keeping in mind that those 2 are somewhat common. I think everybody knows this. I'll just run through it, sort of how these present. The classical presentation, right, is recurrent bacteremia and or meningitis, usually from these encapsulated bacteria. The early pathway tend to be strep, Haemophilus, but also Neisseria, whereas the late pathways are almost exclusively Neisseria. And then what I'll come to, and this is not new, but newer, this idea of autoimmunity coming out of early classical complement deficiencies, C1q, C1r, C1s, C2, and C4. And I'll show you where that's going and why that's pretty exciting research. C3, interestingly, doesn't cause autoimmunity per se, but it causes a lot of lupus-like syndromes and bad glomerulonephritis, and that's been an active area of research as to what's going on with C3 deficiency. This is all a little counterintuitive from what you'd expect. But they do not form lupus antibodies. And then the terminal pathway defects really do not lead to autoimmunity. So I told you how rare these are, but actually I think they're a lot more common. I mean, I've found in my first year and a half, I diagnosed at least 6 cases of complement deficiency just by looking. So there are a lot of studies that have shown, or from kind of the 90s and then some from 2000s that, and the one I cite is out of the USSR before that collapsed. But anyway, that up to like 20% of all patients with a single episode of meningococcal meningitis actually have an underlying complement deficiency. I wrote terminal. It doesn't have to be terminal. It could also be early, depending on which study you look at. And then for the ungroupable strains, and in particular the ones where we don't have vaccination against them, it may be as high as 45%, and with recurrent disease up to 50%. So, yeah.
Is it what's the inheritance? Is this all autosomal recessive, or is this a...
Yeah, so except for Piperidin, which is X-linked, these are all autosomal recessive. But again, with C9 and C2, which probably make up the majority of these, if you have a carrier rate of 1 in 70, or with C9 in Japan, it's going to be whatever that would be, 1 in 30 or less, something, pretty low. They're out there, but yes, they're autosomal recessive. So, I saw probably a dozen cases of meningococcal meningitis in residency, and we never checked the CH50 or a C9. So the reason we're not seeing it is because nobody's looking. And then, so this idea, and I'll come to why does early classical complement deficiency cause autoimmunity, but there was a great paper out of Brazil where they just took 70-some patients with initial presentation of pediatric lupus and found that actually 9% of them had a complement deficiency. So, it's not explaining all of lupus, but it probably actually explains some decent amount of early onset lupus. So just focusing a little bit on the early complement and its role in autoimmunity. So these are sort of the reported rates. They're at least this high. So C1q deficiency, you're basically guaranteed to get lupus. C4 deficiency, same idea. A little bit lower in these others, especially C2 deficiency, which I told you is the most common. But quite high. And the problem is when people present with lupus, you may check a C3, C4, they may be very low or something, and then you don't recheck it once they're under control, you're not going to make this diagnosis. And in my view, and this is yet to be proven, but it can dramatically change how you might treat that patient. But there is evidence that if you replace the missing factor, you can basically cure the lupus. So again, something to think about and to we should be aware of in our field, I think. So then comes this paradox of why does complement deficiency cause autoimmunity? And nobody knows for sure. You'd think because lupus, we had a great talk about lupus from our rheumatology colleague a couple of months back, and I liked how he characterized it. Lupus is basically type 3 hypersensitivity gone wrong from your own antibodies against double-stranded DNA and other nuclear antigens. But to have type 3 hypersensitivity, you need complement, right? So the immune complexes fix complement via the classical cascade. That's what causes the kidney disease in lupus, the skin disease. So how is it if you're completely lacking that, you can still get lupus? I may not answer that, but I'll move towards it. So I just put this in because I'd already made these for another talk, and I think they're pretty cool. But it's worth knowing some of the molecular chemistry and the actual crystallography of some of these. So C1q, again, is this really awesome. It's 3 genes. You have C1q, A, B, and C. There's because we like to use all these A's and B's and whatnot in complement. And this is its approximate structure here. So it's hexamer. These are C1R and C1S bound in the middle of it, which are the catalytic domain. One thing worth knowing about C1q is that, as opposed to all other complement pieces, it's made in the bone marrow. So bone marrow transplant could theoretically be curative for this. Also in monocytes, and that's as opposed to the liver, which other ones are made on. And that's basically what I would say about it. And that's going to cleave C4, as you know. This got cut off. I tried to fix that. That's annoying. So this was a really cool paper that came out in Science just in the last year, and I just put it up there as sort of, advertisement for complement. It made one of the lead articles of Science, where they basically showed, this is cut off, but they showed in sort of beautiful crystallography how C1q works. They were able to show that, in fact, IgG, through non-covalent bonds, makes this hexamer. So you get, when IgG binds on the surface of bacteria, you actually get 6 IgG molecules binding together in this circle, and that's what C1q can land on. And they showed exactly what amino acid in the constant chain of IgG is responsible for this, and the reason the paper had such high impact was the idea that if you start changing these, you can completely change to what degree immunoglobulin activates complement, either making it more active or less active. And in the world of sort of designer monoclonal antibodies, that could be really critical if you want to activate complement or not. So for the first time, we've known about this for 60 years. For the first time ever, we actually learned how this interaction works. They had some really cool pictures in that article. So C4, I won't run through this, but is basically this much smaller molecule that you have a pro form, and then this is what's actually cleaved. So this C4A that floats away is this little piece, and the C4B, which forms C3 convertase, is a much larger piece. I'm going to skip this. C2, basically the same idea, that it's enzymatically active. So then, getting back to how does all this cause autoimmunity, or does it cause? I mean, some people still debate whether this is causative or just associative or what. So there are a number of theories. So if you don't have C1q, if you don't have C4, you really can't clear immune complexes. That's sort of what's been around in the field the longest. Basically, immune complexes build up. You can see in C1q deficient patients they have higher levels of immune complexes. And so rather than clearing those by the typical pathway with monocytes, they're picked up by dendritic cells and present self-antigen, and you lose breakdown tolerance. What doesn't make sense there is if you give people C1q back, why do those autoantibodies go away? But nevertheless, so this is the idea, and then eventually you have such a buildup of immune complexes, presumably you activate the alternative pathway in the kidney and elsewhere, and that's sort of what causes the pathogenesis of lupus. Sort of on the same idea is this inability to get rid of apoptotic debris, and that leads to a breakdown of tolerance. But perhaps what's most exciting, and finally there's some literature to support this, is that you basically have a failure of B-cell tolerance. So as I'll show you, the complement cascade really is informing adaptive immunity in very intricate ways, and you need C4 for B-cell negative selection. Without it, you basically start making all of these autoreactive B cells. So this is sort of getting into my expanding role of the classical. This is still sort of classical roles of complement we've known about for a little while, but where they're doing a lot more than just host defense. So basically, C1q has been shown to be critical for clearance of these immune complexes as well as apoptotic debris. C4 is really critical in tolerance, and I'll show you a slide to that effect. And then C3d, this is some really cool work that's basically the next enzymatic cut of C3b, is critical to antibody production. So again, really B cells are going to be dependent on C3 and C4. So this is something that has sort of been appreciated but was forgotten in the field and is now becoming hot again, at least in my view, and my research is sort of moving this direction, some of it. So how complicated the genetics of complement are, and I'll just give you the example of C4, which is both the coolest and the most complicated, and something hopefully everybody will know by heart at the end of this. C4 sits in what we call the MHC class 3 region, which is only named that because it's between class 1 and class 2. There are no MHC genes in there, and because it's loaded with immune genes. This is a super oversimplification of that region, but here you have the HLA ABCs, you have the DRs over here, DQs, and between that you have the MHC3 region, which has, these are just a few of the immune genes in it, and focusing on the complement, you have C2 in here, you have CFB, and then within this area, what's called the RCC complex, you have C4. This is the most gene-dense region of the genome, the whole MHC region is, and the MHC3 is the most gene-dense of the most gene-dense region, which is curious. That's what that says. So you have a lot of immune genes in here, and in this RCC complex, you have these 4 genes, and I'll focus on C4, but it's a pretty cool region. You have, blue is C4, so this is your traditional allele. You have each of these 4 genes, C4, and then these other 3. But because of June Deep, and then so just to make it complicated, you have multiple versions of C4. You have a C4A, which is acidic, it's a C4 big A, a C4 big B, which is basic, completely different from C4 little a and little b. And you have a long and a short, because you can have this black, which is a retrovirus you can have inserted in C4, and each of these C4s has different properties, different half-lives, different catalytic activity. And because of recombination events at this point here with the CYP21A2 gene, you can basically get bimodular complexes, so you can get 2, you can get trimodular complexes, and you can have all these different combinations. You can have a long, a short, an A, a B, and you can basically have anywhere from 0 to 4 copies on a single chromosome of 4 different kinds of C4. So this is what you're left with, anywhere between 0 and 8 copies of C4, 0 to 8 copies of each of these different types, C4 big A, big B, long, short, and it gets tricky. And what does that all mean? Well, basically they've shown that the number of copies you have, a paper out of China looking at a lot of different patients about, 2-3 years ago, basically showed a strict dose effect. The more copies you have, the more C4 you have in your serum, which is probably why we have such a broad range of normal for C4, anywhere from like 10 to 50. But nobody really looks at that in terms of disease at the protein level, but people are starting to look at the gene level. And basically what was shown from a group, so for those who do genetics, it's very hard to get a gene copy number in the chromosome. But there are techniques to do it, and these guys did exactly that. This was, again, about 5 years ago. Looked at what is your risk of developing lupus based on how many copies of C4 you have, and they showed a perfect sort of dose-response curve. The fewer copies you have over here, the higher your odds ratio of lupus development, and the more copies you have, the lower. So sort of leading to this idea, and I'll see it again with complement factor H, that this is not a simple, do you have the gene or you not, is it autosomal recessive? Rather, this is really sort of how many copies do you have, how many are functional, and what are each of those copies doing in terms of your risk of disease. So the genetics become much more complicated than we sort of ever imagined. Just to further support this idea, because nobody actually knows if C4 deficiency is causative of lupus, but there are other things in the literature to support it. So we all know and love C1 inhibitor deficiency. That's a perfect example of acquired C4 deficiency, because while that's not the cause of the angioedema, it's a side effect, and those people, those patients are at higher risk of development of lupus, presumably through the acquired C4 deficiency. And back in the 60s, they were actually trying to give C4 as a treatment for hereditary angioedema, which which of course didn't treat the hereditary angioedema, but it may have prevented lupus. I'm going to skip that. So, 2, and this slide is tough. I was trying to figure this out again last night, but this is a group out of Boston, Mike Carroll published last year, basically showing why you need C4 to delete autoreactive B cells. And I won't go through this in a lot of detail, but they basically took mice who didn't either had C4 as a control or didn't have C4, and they transplanted them with different bone marrows, either C4 replete or C4 or without C4. And then on the background of this genetic phenotype that's basically going to cause the production of self-reactive B cells. And the take-home point is that if you don't give them any C4, which is this last slide, you cannot delete self-reactive B cells, whereas if you give them even just a little bit of C4, so 10%, this is being made in myeloid, because normally C4 is largely made in the liver, but even just a little bit of C4 seems to be enough to delete these self-reactive B cells. Again, just sort of the first proof of how apparently C4 is leading to effects on B cells and basically adaptive immunity. So a little bit of C4 is critical for deletion of self-reactive B cells in mice and presumably in humans as well. So that's my update on all the stuff you were already supposed to know about complement.
Right.
Move on to the regulatory proteins, which has been the definitely hot area. When people say complement is hot again, I think this is what most people are talking about. So here are some of the regulatory proteins. C1 inhibitor, we all know. I'll go through that again briefly. But all these other ones as well, which have been implicated in diseases really over the last decade or more that nobody would have guessed. So let's just start with, again, what we all already know, just to keep people sane. C1 inhibitor. So this was discovered quite a while back. C1 inhibitor is critical for inhibiting C1, the C1 complex, its enzymatic activity. Though also, my next slide, it does other things too in the coagulation cascade and with bradykinin. This is borrowed from my talk on this 2 years ago, so I'm sure you all remember the history in great detail. But basically, bradykinin is a key molecule that was discovered decades ago and what we're sort of targeting. It's worth everybody knowing the pathogenesis of C1 inhibitor. They couldn't call the gene C1 inhibitor, that would be too easy, so SERPING1. And its normal function is to inhibit the enzymatic portion of C1, namely C1R and C1S, but then also the early parts of coagulation at factor 12. And the exact mechanism is not entirely known as to why that leads to angioedema, though in the end it's really through bradykinin generation. So this is a slide I've shown before, but a nice New England Journal summary of what C1 inhibitor does, and then where all these new drugs act, which we have. So the part of the complement cascade, which is unrelated, is over here, blocking C1, catalyzing C4 and C2. What's more critical is this part over here, where C1 inhibitor is basically necessary for in bradykinin metabolism, and without it you have excessive bradykinin metabolism with a slight trigger, and that's what leads to the angioedema through bradykinin receptor. And of course we have a variety of molecules, 3 different types of C1 inhibitor which replace that. We have a catabant which blocks the sort of terminal step of this, bradykinin's interaction with the bradykinin B2 receptor. And the reason that's hot is simply because we have the treatment for it. So one thing that I think people don't often think about in this, while it is genetic and autosomal dominant, it's actually quite high rates of de novo mutation. It's kind of a hot spot. So probably a quarter or more are de novo, and hence you really don't need a family history to make this diagnosis. Of course, we all know it's frequently delayed in terms of diagnosis, and it's kind of more common than you might expect. I mean, this is sort of the frequency of lupus, 1 in 30,000. So, you know, that's the low or the high end of it, up to 1 in 150,000. But there's more out there than certainly the average internist, primary care doc thinks about. And it used to have a very high mortality. It often presents early, but it can present in more of sort of the teenage or even adulthood time. Usually affects just the skin and the GI tract, but basically will eventually affect the larynx as well. So even if somebody's never had a laryngeal attack, that doesn't mean they won't, and you shouldn't treat them in anticipation of that. There are a number of triggers, mostly trauma, but also stress-type responses, and they really respond in no way to our conventional anaphylaxis drugs. Some pictures of it for those interested. And basically, again, there are the new treatments, so C1 inhibitor, bradykinin receptor antagonists, and kallikrein inhibitors. This is an older table. I was just corrected by Art that one of these, so the recombinant version is, I guess, now approved in the US as well. But we have a number to pick from. Still, the only one you can use in kids is Berinert, right? Which is annoying. I know at Catamant they're doing a trial in pediatrics. Right now it's down to age 16. I don't know what the current update on that is and when we'll be able to use that in kids. It would sure be nice. There's somebody in Eastern Washington who's involved in that trial. But these are all incredibly safe and fairly effective. I'm not going to go through the efficacy data, but pretty effective drugs for this condition. And I think we're all using them a fair bit for the patients we do have. So,
we're trying to get inserted children's down 4.
Which one? Berinert, yeah.
No, Cabot.
Or Catamant, I mean, yeah. Down to age 4. There is a trial in place to do that. So, moving on and to the other regulatory proteins. So again, I think everybody's probably at least heard of this, but maybe doesn't know the details. And I think it's worth knowing. I got at least a handful of calls my first year as a fellow from nephrologists saying, hey, this kid's got this aHUS, what do you think? Is it complement? What can we do about it? I don't know if they're still calling or if they've sort of read the literature enough on their own, but my experience was that especially adult nephrologists, and to some extent I was getting Swedish pediatric nephrologists calling me, they really don't know this. So basically these 3 factors which put the brakes on the early complement cascade. So before you get to the terminal one, factor H inhibits this C3 convertase, CD46, factor I, basically being critical to slowing down the activation of C3, cause this, again, who'd have thought, disease of atypical hemolytic uremic syndrome. So for those who are a little ways out of their sort of medicine or pediatrics training, just a reminder of what this is. It is basically this microangiopathic hemolytic anemia, largely happening at the site of the kidney and leading to acute renal failure and really end-stage renal failure if untreated. But the typical triad is hemolytic anemia, thrombocytopenia, and acute kidney injury. It's always been thought to be a pediatric disease, but in reality, probably about half of these are first onset in adulthood for whatever reason. Usually, so this is in contrast to typical hemolytic uremic syndrome, which is caused by Shiga toxin, E. coli. This is without that inciting event. And it's probably actually more frequent than the E. coli version. It's thought to be triggered by some kind of infection like a URI or some immune stimulus like pregnancy, but nobody really knows. And you may pick up on these kids because they have chronically low C3, but you may not, and that really doesn't rule it out. And if you don't treat it with the new drugs, basically you have rapid progression to end-stage renal disease and or death. And basically the big breakthrough was people found this association, I don't know when, 10 years ago or more, with complement factor H. And initially it was thought you had to have homozygous loss of both, so it was autosomal recessive. But in reality, there's a dose effect, just like we saw with C4. So if you have only a single copy of CFH, you're still at pretty high risk of developing this. And basically, so far, if you take all the atypical HUS out there, somewhere between a quarter and a half of it seems to be due to factor H deficiency of one form or another. But then more recently, people started looking at all the other proteins, so now they've found factor I in 5 to 10% of it, CD46 and some amount of it, less than 10% so far. And then curiously also, as you might expect, if you can't, on the one hand, not being able to stop this, but also if you have overactive C3, so people have found gain and function mutations through SNPs and C3, or even complement factor B, which causes the alternative, this is, I didn't say, but a derangement of the alternative pathway, excessive alternative C3 convertase. And then also now there are antibodies being found in complement factor H, which are probably pathogenic, so it can be an acquired disease as well. And you basically get uninhibited activation of the alternative pathways through C3, CFB activation, causing the alternative C3 convertase. Nobody knows exactly why this is happening in the kidneys and what's the issue, but the idea is that if you start with some minor insult, the kidneys are very fragile, the endothelium within the kidney, that leads to activation of coagulation, that leads to complement activation and thrombotic microangiopathy. And basically, the breakthrough was, so eculizumab actually already existed. I'll come to why eculizumab was created. But it's a monoclonal antibody against C5, so just downstream of the C3 convertase. So C3b C3 complexes with factor B both get cleaved to C3b, BB, and then another C3b comes in. That becomes your C5 convertase in the alternative pathway. Normally, C5 would come down, be activated to get the membrane attack complex. Eculizumab binds C5 in just the right spot where it can't sit down in the alternative pathway C5 convertase, and basically prevents the terminal complement cascade from being activated through the alternative pathway. And people tried this in atypical hemolytic uremic syndrome. This was reported in the New England Journal about a year and a half ago. They had two cohorts, 17 and 20 patients. This was open label, not randomized controlled or anything. The FDA approved it because the response was so dramatic. Basically, this is an untreatable condition. People use plasma exchange hoping it will work. It can work a little bit, but a lot of people are refractory to that. The idea there is that you're replacing factor H, probably. These guys had a dramatic improvement. It's hard to see this, but if they looked at kidney function and then platelet count as their outcomes, showed dramatic improvement, and subsequent to that, people have also shown dramatic survival benefit. So basically, it's a life-saving drug for this condition. And again, this is a condition, unlike the typical one, that's going to relapse over and over again if untreated. So these patients are being put on this drug for life at Q2-week dosing. It's about $500,000 a year. The two most expensive drugs in the world right now are C1 inhibitor and this. So this is, affecting complement's not cheap. But it's dramatically effective. And so who to treat with this has been changing, and I didn't know this when the nephrologist called me, but I've subsequently figured it out. Basically, you treat anybody unless there's clear evidence that this is not atypical HUS. In other words, you don't have to get a genetic diagnosis because it's almost impossible to get a genetic diagnosis. There are now two labs who will do it for you. One is in Germany, one is in Cincinnati. I don't know how accurate the one in Cincinnati is. The Germans have started doing, I guess on a clinical basis, factor H and factor I. But even there, there have been, I forget, but many mutations described. It's not always clear whether they're pathogenic. There's variable penetrance. So whether or not getting genetics is useful, that's to be decided. But basically, if you've ruled out the things that look like atypical HUS, namely you've ruled out that this is E. coli induced, and you've ruled out TTP, which is due to a deficiency of Adams TS13, then you should treat, is the current guideline. And I guess the Germans, when they had this last outbreak of E. coli 104 or whatever it was, they started treating people with E. coli-induced HUS and found this to be effective as well. So that recommendation may go away also. Expensive drug, frequent dosing. I don't know if that should be there. I tried to fix these the other day. So we're moving on now to PNH, paroxysmal nocturnal hemoglobinuria.
E. coli treatment, did they just need 1 or 2 doses then?
Yeah, presumably. I don't actually know how long they were treated for. A few doses, but they stop. They don't need it lifelong.
Matt, how much of that genetic variation can be done by the genome analysis that's popular and available now?
Oh, like whole exomes?
Yeah.
So some of these are due to factor H mutations. You'll generally miss that, or sorry, factor H deletions. You'll miss that on whole exome sequencing because you don't really get a copy number from whole exome. Presumably the point mutations you should pick up. So people who are getting, but I mean, it all depends on what depth you're doing. Presumably, you should pick this up by whole exome sequencing for the most part. But again, it's one of those ones where there's variable penetrance. We don't know what a lot of mutations mean. So it's going to be one of those ones that just gets super confusing if people are getting whole exome sequencing. They find a mutation in this, but they've never had disease. Do you start them on the drug? Do you not? The answer will be you don't, and you just watch closely. But nevertheless, the variable penetrance question
Do
is
these
tough.
people all have a decreased CH50, or are they going to have normal complement screens?
No, so this is an alternative pathway defect. You can have low-ish C3 values because you're basically constantly turning over your C3 a little too fast. So your C3 level can be low. They've described that mostly in the homozygous CFH deficiency. But otherwise, they're going to have... I don't actually know what their aH50 looks like. You'd think it might also be a little low, but probably not a huge amount. So the typical teaching is you don't pick it up by those screens. And so I guess the idea is have a low index of suspicion for this in a kid, or in anybody, a kid or adult, with this sort of presentation. I mean, I have to say, I doubt if any adult nephrologist, when they see a case of HUS, if they think about getting genetic diagnosis or the risk, just like with complement deficiency, ID doctors don't really think about testing CH50s in those who have a single episode of bacterial meningitis. If they have a single episode of HUS, they'll probably say, well, you probably ate a Jack-in-the-Box, let it go. But I don't know. So I think it's worth us knowing about it and being on the lookout for it. So PNH, again, the idea that these regulatory proteins are critical. CD55, CD59, critical proteins in basically slowing down, in particular CD59, which is what's really critical in PNH, the formation of the membrane attack complex in the terminal cascade. So what is PNH? It's a disease we've known about for a long time, and I think actually the pathogenesis was worked out quite a while back. But basically, for the most part, it's felt to be an acquired mutation. So it's usually an adult onset disease in this PIGA gene, which is on the X chromosome. So a single somatic mutation is enough to cause this disease because the other X chromosome is silenced. And basically what happens is you mutate it in a single hematopoietic stem cell. That expands enough to become a large enough clonal, not even really clonal because you may have other mutations, but a clonal-ish hematopoietic stem cell, which is basically lacking this gene. This gene is necessary for making this anchor protein, which is on red blood cells, but also PMNs and other cells, and anchors a lot of different proteins to the cell surface, but one of the critical protein, or two of the critical proteins are CD55 and CD59, which are needed to put the brakes on complement at the cell surface. So you have CD59 anchored. If you lose that, you basically have activation of complement on the surface of red blood cells, which can't be stopped, and hence you get a hemolytic anemia. The typical presentation, how it was named, of red urine, you don't have to have that. That's maybe present half the time. That's part of the name. And then paradoxically, you get this intense thrombosis. So people often actually present initially with thrombotic events before anybody's picked up on the fact that they have this sort of chronic low-level hemolytic anemia. Classically, it's Coombs negative because you don't need antibody. This is complement being activated by itself in the absence of antibody. but you should have C3 fixed on the red cells. So if you look specifically for C3 in the absence of IgG, you will find it. Here's what's going on. So basically, normally the C3 convertase activates C3 on the surface of the red cells, but you have these guys blocking it. And in PNH, this leads to an intravascular hemolysis of the red cells. You also, though, have C3 opsonization of red cells, and then in the extravascular space, so the spleen and so forth, you have macrophages removing red cells. That's not going to be blocked by eculizumab, because that's not terminal complement mediated. It's adult onset. Most patients present after the age of 30. It's one of these things that's traditionally considered extremely rare. So when they made eculizumab, it was for this. There were like 100 cases in the world or something, I don't know. But the thought now is it's probably underdiagnosed. I don't know if that's just a drug company telling me that or if it's true, but it's out there. There are also rare cases that have been described as with all complement genes of congenital homozygous, so autosomal recessive CD59 deficiency. This is what you need to know to diagnosis, FLAIR, which is a type of flow cytometry looking for that GPI anchor, and you have to run it on both RBCs and PMNs. Most labs have their own variants. Some labs don't know how to do this, but because you've destroyed all your RBCs, you may not see it if you just look on RBCs. Basically, this was the sort of landmark trial that came out now almost a decade ago that got eculizumab approved in the first place, that you have a marked decrease in hemolysis when you treat with eculizumab versus placebo, and you can basically save these guys lifelong transfusions. You'll note, though, these guys still continue to, you're looking at the time to first transfusion, and you'll see that these guys still continue to hemolyze. And the thought for that is because they continue to have this extravascular hemolysis in the spleen, which is not mediated by terminal complement, but rather simply by opsonization with C3b, C3d. So it's not curative, it just slows things down. And of course, that generates excitement of making another orphan drug for a disease of 100 people. So the limits are exactly that. It blocks intravascular but not extravascular hemolysis. And of course, the other problem with this is, and it is a real problem, you basically make these guys terminal complement deficiency patients. So they're at significantly higher risk for bacterial meningitis. There have been numerous case reports of that. People get hypervaccinated. They're sometimes put on prophylactic antibiotics. And then there's this whole population, which has largely been described in Japan and parts of Asia, who have a genetic polymorphism in C5, such that eculizumab can't bind that critical portion of C5, and they're completely refractory or largely refractory to eculizumab. So I found this interesting. Just a few months ago, there was a publication, probably by the makers of Cinryze, that C1 inhibitor is probably adequate to treat this. It was just an in vitro study, but basically showing that it's capable of blocking in vitro the erythrocyte lysis from 6 different patients. And I assume they're going to try this in some sort of clinical setting. And then there's another group making an anti-C3b monoclonal antibody, which I guess I think I have the name of that somewhere later, which would presumably also block the extravascular hemolysis because that's mediated by C3b conversion to C3d.
Pat, the N in that is nocturnal.
Nocturnal.
Why
Yeah.
is this disease named that?
That's historical again. Why they saw more of this hemoglobin spilling into the urine at night. I don't really remember why that is, and I don't think it's true. But I don't know. You have to look that up.
Just concentrated in urine.
Yeah.
Maybe just concentrated in the urine.
Could be. Now that we keep all our houses warm, you don't see that. I'm not entirely sure, but it may be. Yeah, sort of cold induced. So that's paroxysmal nocturnal hemoglobinuria. Back, still on this role of regulatory stuff and now getting into more common. I don't know this literature in a ton of depth, but have heard about it numerous times, so decided to read about it. Now, all of a sudden, they're attributing age-related macular degeneration to defects in complement regulatory proteins, in particular factor H. this was first, the idea sort of started because so basically what is AMD? It's this disease of the central retina. It's the leading cause of blindness, adult blindness in the developed world. And you basically have these formation of extracellular debris in the retina, which leads to damage to the retina through various partially known mechanisms. And they basically found there's a lot of complement in these. So they were finding complement fragments and the like when they would look at these, I don't know, through biopsies or autopsy specimens or whatnot. And then, based on that, people simply found from these large genetic studies that a number of polymorphisms in complement genes, so first it was complement factor H, this is the main polymorphism, which has been clearly shown to decrease the inhibitory function of CFH, increases your risk in a sort of, again, dose-dependent manner. Heterozygous carriers have a risk 2 to 5 times, homozygous 3 to 7. And then they also found SNPs in these other genes, so complement factor B, C3, which are all, pretty well associated. And normally I wouldn't put a lot of stock in those off of GWAS studies, or I don't know if they've done any whole exome now, but people have been excited enough that they're actually moving forward with trials of trying to block complement in a goal of preventing worsening of AMD. And eculizumab has already completed a phase 2 trial, which I guess they have results of. They're not published, but maybe they've been presented at meetings, where it certainly felt to be safe enough for adults who are otherwise healthy to take this expensive drug, and they're planning to move forward with a phase 3 to see how effective it is in basically preventing progression of AMD. The same end, given the expense and the inconvenience of that, people are now, this is I think a Japanese group or something has made this drug, Zimura, which is a not small molecule, but a non-monoclonal antibody C5 inhibitor, specifically targeted for age-related macular degeneration. So, interesting. I don't totally believe it. I don't know that the mechanism has been worked out in enough detail, but that's never stopped people before from moving forward. So, I'm going to skip this, the CFH-related proteins, basically just telling you there are a lot of other regulatory proteins out there that we don't know anything about that are being linked to disease. There are 5 CFH-related proteins, some of which have already been linked to lupus, among other diseases. And now, all of a sudden, rather than C1 through 9, here are the genes you definitely need to know by the end of this talk, and where they are in the chromosome, what diseases they're associated with, and I only put in the diseases I've talked about. There are about 20 other diseases, quite a few other diseases where people have at least made linkages. So there's more out there. But basically, you have a variety of key complement proteins, regulatory proteins, receptors. One that's really interesting, I think I'll talk about the CR2 complement receptor 2, also CD21, and its role in CVID. Which brings me back to this idea that complement is not simply an effector arm of the immune system. Rather, it's critically involved in informing the adaptive immune system. And at the Quad AI this year, there was a great talk about this as to, why is this? Well, complement is the most ancient part of the immune system other than barrier or skin barrier and stuff. And basically, the adaptive immune system evolved based on complement and other parts of the innate immune system. And, it's really integrated it critically in how the adaptive immune system works. And without it, the adaptive immune system doesn't work. And a couple of key examples of that, so this is sort of being discovered late, even though it's probably the more critical role of complement, or one of the more critical roles of complement. So again, a lot of this work is being done in Boston by Mike Carroll, but he had a paper that came out a couple of years ago, 2-3 years ago, basically showing that without C3, and in particular without these little subfragments of C3, you can't make B cells. He specifically showed that C3d, when complex with antigen on the B cell receptor on an immature B cell, interacts with complement receptor 2, CR2. Without that interaction, basically you do not have, it's essential co-stimulation for B cell maturation. Without that, you will not mature your B cells. Or actually, I think before that, I don't remember what was the order of discovery, but there's this very rare deficiency of CD2, also called CD21 deficiency, which leads to a severe form of CBID. Basically, you have very few or no B cells, and looks like a gamma globulin deficiency. So again, basically showing that this is a critical part of co-stimulation for development of B cells and effector B cells and memory B cells. I showed you this slide before without walking through it in detail, but now that same group has shown that in addition to needing complement C3d for development of B cells, you also need complement then to delete self-reactive B cells. C4 seems to be the critical one here. The mechanism is not worked out, but at least in mice, without C4 or adequate amounts of C4, you have this explosion of self-reactive B cells. So it's involved in both stages of B cell development. And then, now the new exciting part, a year and a half ago, 2 years ago, people discovered, nobody had looked before, but turns out complement is inside of all of your cells. Neurons, T cells, a variety of stuff. It's really being studied at T cells right now. And basically, you need it for T cells to survive. So there's sort of this homeostatic, tonic activation of C3 in T cells. Without it, the T cells don't live. It's totally independent of what we typically think of the complement cascade. It's not activated by C3 convertase, but by a totally different enzyme, cathepsin L, CTSL. Here on the left, you're sort of seeing it being, it's sort of active in a low level, but then when you stimulate the T cell, in addition to it being activated within the cell, it's moved to the cell surface. That's what you're seeing here, co-localization of CTSL and C3 at the cell surface, and seems to be doing a lot of different things on the cell surface in terms of T cell growth and survival. This is just a basic cartoon of what people think is going on, but basically the intracellular C3 is critical for making, this shouldn't be a big arrow out here, but the C3b just goes to the surface, interacts with one of these regulatory proteins, the one that's on the GPI anchor, CD46. Sorry, this is not an anchor protein. This is a intracellular, or a cell membrane protein, CD46, and it's critical for Th1 induction. If you're missing that, you get recurrent infections. This is part of the idea for why C3 deficiency is so much worse than all the other complement deficiencies. You don't get a good B cell response, you don't get a good T cell response. On the other hand, if you have altered signaling, whatever that may mean, you then lose Th1 contraction. So after an initial immune response, they never contract as they should. And the thought is that that may predispose to other autoimmune conditions, including rheumatoid arthritis and MS. So intracellular complement, key in T cell development. And now the new hot idea is that there's this whole intracellular complosome. We've got the inflammasome, now we need the complosome. I'm not going to walk you through this slide, but there's a nice Nature reviews from Claudia Kemper talking about this and all the sort of intracellular function and how it's, this was on my table, but two key proteins, C5 alpha receptor, C3 alpha, or C3a alpha receptor, as being a part of that. I'm not going to walk you through this, but just showing you how complex it's getting, all this crosstalk between complement and various other signaling pathways within the cell. And just to bring it all home to our bread and butter of asthma, this was a great talk at Quad AI. I just borrowed from the paper that it's clear that complement is regulating Th2 response as well. And this is still just sort of at the level of association, but it's been noted basically, these fragments that float away from C3 and C5, C3a, which we think of as an anaphylaxitoxin, and C5a, which we think of as a chemoattractant. The different levels that you have based on allergy or infection-induced stimulation in the airway seem to associate with your Th2 response and your asthma development. So if you're higher on C3a and your C5a low, you get a Th2-driven response, whereas if you're the opposite, you have a high C5a and a low C3a, you actually get a Th1 and T regulatory response. What all that's going to mean is still in the works, but again, sort of showing that clearly these are doing more than we ever thought in terms of driving T cell and cellular immunity. So, hopefully you're now much more confused by what complement does. It was discovered, as we all know, just as a simple effector arm. We thought it was rare, it's actually common. Partial deficiency is critical. It's not all just about, homozygous loss of function. Regulatory proteins underpin a wide variety of diseases we never knew. It's been there a lot longer than the adaptive immune system, and it's, in my mind, David won't like this, but controlling the adaptive immune system, not really, but critical to it. So we got to think about it.
So Matt,
Yeah, that's it.
so you talked about complement deficiencies. Are there any diseases of excess complement?
Yeah, so there are. The prime example, I guess, is, so with atypical hemolytic uremic syndrome, that in many ways is excess complement. While one is loss of regulatory protein, hyperactivation of C3 also leads to that disease. But I think you're getting at more simply if you have too much C4 or too much C1q or whatever, is that a problem? Not that I'm aware of. And, you'd think, because these people with 8 copies of C4 seem to be okay. Maybe there's some later disease we haven't discovered that's associated with high levels of C4, but not unknown, and it seems to be okay. But the argument that Mike Frank made at Quad AI was indeed, this is all sort of a dose-dependent thing. Too little and maybe too much, it's going to be a problem.
So if C4 is critical for SLE, let's say, why don't people with HAE have higher incidence of that, or is there increased incidence of glomerulonephritis in HAE patients?
There's a report. It's reported that both are higher in HAE, lupus and glomerulonephritis in the absence of lupus. Those are older papers for the most part. There hasn't been a lot published on that in the last 20 years that I'm aware of, but the association is there in the literature, and it was sort of noted. I've never seen it myself, and I don't know for sure, because these people normally have reasonable levels of C4. So maybe if you have HAE plus low C4 copy number, that's what pushes you over the edge. I really do think it's sort of a dose-dependent thing with C4. That seems to be
two HAE patients. One died of renal failure, another one's on dialysis, and I had a hard time finding something on German literature where the complement things are involved with the kidney problems.
Yeah. It's basically at the level of case report and case series. It's been published, but
is anyone developing recombinant factor H?
Factor H. So that's a good question. That, I think, was actually how they first were going to try to treat atypical aHUS before eculizumab came on the market, because that's effectively what they think plasma exchange is doing. It would probably only treat one subset of atypical aHUS, but I don't think it's moving forward. It was an idea.
So there's simple organisms that don't have an adaptive immune response, that just have innate.
So the adaptive immune system started to evolve at the level of cartilaginous fish. So I think sharks don't have any adaptive immune system, whereas everything more evolved than that has some adaptive immune system. But they have complement.
They don't have T cells and B cells?
I think. Yeah, they don't. Is that right? That's what I learned. I remember learning that somewhere along the way.
The C3A has been associated with airway hyperresponsiveness. When Marshall Wills-Krebs, she did some interbreeding of mice that either had airway hyperactivity in methicillin or some genetic strains didn't, and she did 50 different strains that she cross-matched, and the one gene that came up that's associated with airway hyperresponsiveness was the increase in the C3A.
Yeah.
Which was the same mutation. Had a paper with the Th2 response.
Right. I don't know the mechanism there. It's probably both the effect of C3 in terms of as a vasodilator and so forth, but also the T cell. So when was that described? A while back? Yeah, this has all been in the last year and a half or recent.
Yeah, that paper was probably 5-6 years ago.
Yeah. No, it's interesting. There's a lot to determine about what's going on here. So far, it's sort of been they've observed it, but why and what to do about it.
If you're going to do a complement screen on a patient for immunodeficiency, what would you order now?
I guess it depends what you're looking for. We still typically say, there are things I didn't even talk about here, if you're going to do a graded approach, so if it's recurrent sepsis, meningitis, I start with just a CH50. If that's normal, I'll usually go for an AH50 as well, and a C9 potentially, especially if it's like recurrent meningitis. I do think measuring a C9 is important. So CH50, then AH50, and C9. And then if you're still particularly concerned, I'd look at the National Jewish Catalog, where they have different, you can do early, the early pathway screening, the late pathway screening, you can do particular levels of each protein, but those are the first two. And then this idea of MBL, which I didn't even talk about. So, 10 years ago it was thought that MBL deficiency leads to recurrent infections. That kind of died out when they realized how frequent MBL deficiency was, like 5% of the population. But now the thought is that MBL deficiency along with something else, whether that's partial defect in the complement cascade or the like, may actually be a cause of recurrent infection. So I don't measure MBL levels, but I've seen it done.
One more question, I keep bugging you, but in the old androgen literature improving the treatment, did that affect complement? Or did that affect actually production of C1 esterase?
Well, I think the idea there is that you give it increases liver output of C1 esterase, C1 inhibitor. And I don't know if they've actually measured the level to show that. It makes sense because most people who have C1 inhibitor have one normal copy. Again, that's a dose-dependent thing. You need 2 copies to have enough. There are rare cases of homozygous deficiency, and those people presumably would not respond to it. But the idea is you're just increasing the level of the good copy with androgens, I guess.
So it didn't measure whether it was C3A or C5A that was going up or down when you did that?
I don't know what they measured. I would just measure C1 inhibitor level and see if it goes up. I mean, most of these patients who are type 1 HAE have 0, have very low levels, probably because it's being consumed. So hopefully you bump it up so there's some level, or have low, they have low. So presumably that's what you're seeing. I've never measured it or seen that was done.
When you were looking at HAE, has anybody made any progress in finding a bioassay for what we call type 3? Anything to measure?
I didn't look into that. There were a lot of posters at the Quad AI about it again. This excitement about factor 12 seems to be dying out. Right. Yeah. It's never been described in the U.S. It's been described in a variety of European countries.
Could you remind me what MDL is?
Mannose binding lectin.
It's a lectin binding.
Yeah. Yeah. It activates the third portion of the complement cascade, which I didn't really talk about today, the lectin pathway. But it also acts through, they all converge to C3, but it acts through C2 and C4 like the classical. So it may, it may be that if you're low on that plus low on classical protein C4 or whatever, that
excellent job. I think
that's
the best complement stuff I've ever heard. They're the most understandable.
When looking at that slide, it would seem like C3 deficiency would be lethal.
It's the worst disease. Why it's not lethal, but it is the worst of all complement deficiencies, and also one of the rarest.
When you were looking, I don't know if you looked up at the history, but when I was way back when at the NIH, I was taught the guy who discovered inherited committed suicide because he was a beginner in the field and classical people told him he was wrong. There was no such pathway.
Yeah. remember that. I've heard that. I don't know if it's because you told me or because I heard it.
I think that's true. I can't remember the guy's name, but a man named Hans Mueller Eberhard was the guru of compliment at that time. Told him that was
I still don't understand it, but that's the closest I ever got. That's pretty cool.
You're just
So,
there's a lot going on.
yeah, it's just,
I
it's
did.
but there's way more than we don't understand.
okay. Good.
Something you're going to do half your life, you got to get
Very nice.
Three of us plugging things in, and I also have a transformer. Most modern things don't need a transformer.
Coming back to our
Without
I'm
anything.
sorry, I have to. My mother's from Irish.
I've forgotten that they all come to you.
I know, that's like me. If I didn't work
He's got to give me a little update on his.
On the IRBs.
Good. I'm surprised you didn't.
Well, you just got to know. So, the bacteria angioedema type 3, factor 12.
You can send them if you want.
Your dad doesn't know what to do with them either.
I'll treat them. I'm more.
How do you treat them?
Or I mean, I'll see them. I'll talk to them.
All right. I was going to say, how do you treat them? I need you to tell me
I just
that.
want to make sure I can, because I know you're paying for yourself, so if I can.
And she'll make my brother and sister can live in your but I'm here.
Can I give it to you, or do I need to do it?
No, give it to me. I'll give it to you. She's collecting it for me. That would help. It's somebody who I counted on coming. And then even though I roast people and said, if you RSVP, you're going to get charged.
Because there's one
Can't really
guy
do
from
it.
I'll double it up.
He scheduled 2
Hi, Dr. Altman.
Trixie, hi.
Yeah, yeah.
Is that for me?
Hi, Dave. Oh,
No, no.